now. Okay, so very good. Good morning, everyone, and welcome to the Center for Theoretical and Computational Physics weekly seminar. Today, it is a pleasure to welcome Martin Haase from the De Beyer Institute for Nanomaterial Science of Utrecht University in the Netherlands. Martin did his PhD at the Max Planck Institute for Colloids and Interfaces in Potsdam, Germany. This was followed by a couple of postdocs in the United States, first at New York University and then at the University of Pennsylvania. He then got his first tenure-track position at another higher education institution in the US, Rowan University. And that was before coming back to Europe in 2019 to take up a position at Utrecht University, where he is to this day, and he is also the recipient of an ERC starting grant. Today, he's kindly agreed to tell us about his work on flowing liquids through fluid-bicontinuous gels, which is something which is of much interest to us. Before I hand over to Martin for the seminar proper, just a couple of announcements from me. First, in the interests of internet stability, can I ask all of you, except the speaker, of course, to mute your microphones and turn off your cameras during the seminar. If you wish to ask a question, you are, of course, free to unmute yourself, and if you so desire, turn on your camera. The second announcement is this seminar is being recorded, so by staying on, you're giving consent to your voice and image being recorded and stored. So without further ado, it's over to Martin for the seminar.
Thank you, Paolo, for your kind introduction. I assume you all hear me well. And I want to encourage you, if you have any questions during this seminar, feel free to just interrupt me. You could just unmute your microphone and just shoot the question at me. So let me briefly tell you what my title slide here shows you. Here you see these fibers in the background. I call these fluid-bicontinuous gels. There are two fluids. One is water, that's in blue, and another fluid that is an oil that is shown in green here. And what we have been working on recently is to actually really flow liquids through these fluid-bicontinuous gels. And I'll tell you a little later about that in more detail. So my talk today, first, I will give you a general introduction to these fluid-bicontinuous gels. They are also known as bijels. And then I'll tell you about how we can make bijels have a nanostructure via another method that is called STHIPS. I'll tell you more about that. In the third part of the talk, I will then indeed tell you how we can flow fluids through bicontinuous gels. And last, if there's enough time, I'll tell you about how we can mechanically reinforce these fluid-bicontinuous gels. So let's get started with the first part. Let me give you some example of fluid-bicontinuous networks. Think about your skin, for instance. If you experience an injury, you are aware that your skin will be able to self-repair itself, and that happens via the supply of nutrients to different blood vessels that then allow your injury to heal. And engineers, they try actually to reconstitute something like this in a laboratory by here, for instance, microfabrication of fluid-bicontinuous channels, one carrying a monomer and the other a curing agent, so that a damage can be self-repaired by filling the damaged site with a polymer. Another fluid-bicontinuous network is common to many chemical engineers, like heat exchangers. In heat exchangers, one fluid travels through pipes while another fluid flows around those pipes, and those two fluids may have different temperatures and then thereby exchange heat, for instance, to evaporate one fluid in a chemical or industrial plant. But also another fluid-bicontinuous network we have in our bodies are our lungs. Think of how we inhale air, and then the oxygen from the air is able to penetrate into our blood, being uptaken by hemoglobin and then supplied to our organs. Also, that is a fluid bicontinuous network of an air and blood. And again, scientists, they try to actually mimic this in the laboratory with microfabrication, where they have air channels that pass through this PDMS chip and blood channels through other parts of the chip, and then exchange of oxygen can take place through the PDMS material. But you see, those are all examples of fluid bicontinuous networks that have been fabricated by microfabrication. If such a fluid bicontinuous network should become really on industrial scale, then microfabrication is usually not the choice. Instead, I asked the question, is it possible to assemble such fluid bicontinuous networks via self-assembly in the laboratory? So yes, it is. You may already anticipate this. And my approach to do so is based on emulsions. So here you see a classical example of an emulsion. And you know that emulsions are usually composed of droplets of one phase in another continuous phase. Typically, the droplets have a different density. They will rise and then they are unstable. They coalesce with each other to form one phase. So the interfacial area is minimized. However, you can introduce so-called surfactants or detergents. Those assemble on the interface of the droplets and provide a stabilization mechanism that hinders the droplets from coalescence. So that's a stable emulsion, facilitated by molecular surfactants. But there are other types of surfactants, namely nanoparticles or colloids. They can also, just like the molecular surfactants, assemble at the interface of an emulsion droplet, like for instance has happened here. These are electron micrographs from my PhD thesis, where 20 nanometer silica spheres have self-assembled on the interface of oil droplets and formed a steric barrier on the droplet that hinders droplets from coalescing with each other. So these are particle stabilized emulsions. But I told you that I would like to obtain a fluid bicontinuous network with emulsions. And you can see this is definitely not fluid bicontinuous. The droplets are not continuous, only the surrounding is continuous. So how do you make a bicontinuous particle stabilized emulsion? I show you in this video. This is a microscopy video of a phase separation of oil and water. It's a specific phase separation that we call spinodal decomposition. And as you saw, it generates these intertwined channels of oil in green, for instance, and water in black. But over time, also this system will coarsen, and then gravity will separate the two phases into one layer of oil and one layer of water. What I like to do is to stop this process at an intermediate state so that the separation doesn't get to the final stage, which you see here. And to this end, I'm introducing colloids in an initially monophasic mixture of two fluids. And then I trigger the phase separation of the two fluids. And as a result, the colloids, they will begin to self-assemble at the interface between the two fluids that have phase separated. They will then arrest the structure by a process called interfacial jamming. So here's a microscopy video of this process indeed happening and functioning. You see here that after some time of coarsening, a red fluorescent layer is formed on the interface, which are the colloids that have arrested this structure. And as a result, you get a fluid bicontinuous gel, where both phases, the oil and the water, are intertwined and both of them continuous. So these materials are also known as so-called bicontinuous interfacially jammed emulsion gels, short bijels. The history of bijels actually entails, or it started with computer simulation. Mike Cates and a postdoc, they carried out lattice Boltzmann simulations. And here you see a video of their work, where these green colloids assemble on the interface of spinodally demixing fluids and then mechanically arrest this structure by interfacial jamming. 2 years later, after the first computer simulation, bijels were first shown to be experimentally obtainable in the laboratory. And afterwards, more research started in also the United States. And Jens Harting carried out very interesting computer simulations also to understand more about the properties of these particle-stabilized bicontinuous emulsions. In 2015, I joined the stage as a postdoc where I introduced a new method to make bijels called STHIPS. And later, researchers also realized that this fluid bicontinuous network is interesting for battery applications or membrane separations. And recently, even an approach was shown where you don't need to use spinodal decomposition to get the fluid bicontinuity, but you can actually obtain it just by simply shaking mixtures of oil and water. Nevertheless, if you look a little, it's an interesting field of research, no? But if you look at the numbers of publications per year on this subject, it's not all that much. But I'm very I'm very optimistic, not pessimistic. I'm optimistic that over time, this number of publications will grow because this is an exponential fit. So highly confident. So some open questions about these bijels are, for instance, how can you make bijels with sub-micrometer domains? And the second important question that was already raised at the very beginning in the computer simulations by Mike Cates, how can you pump liquids through these bijels? That would be very interesting for applications of bijels. And last, how can you mechanically reinforce bijels? Because they are very flimsy materials usually, so they need some reinforcement. Good. So let me briefly tell you first about how bijels were made at the beginning. So here you see a binary phase diagram of lutidine, an organic molecule, with water. Above the binodal line here, which is a lower critical solution system, you have regions of phase separation, nucleation, and spinodal decomposition. Now, imagine you start with a mixture that is miscible at a low temperature, and then you quench it by heating it into the immiscible region. Then you're going to form two fluids, one, for instance, water, and the other oil. Now, imagine there are colloids. There's a colloid in maybe at the beginning, the water phase with a radius r. This colloid, due to its surface properties, may actually have an affinity for the interface between the oil and the water. And let's assume this particle has a contact angle of 90 degrees and the interface has an interfacial tension. Then in a very simplistic model, you can predict the attachment energy of that particle to the interface with this formula, where you simply have the area that the particle occupies times the interfacial tension between the oil and the water. This very simplistic model neglects effects such as line tension, of course, but it gives us a good intuition first to understand the process. So now let's take a look. Say you are doing this quench. Then along this increasing temperature line, you will hit tie lines in the phase diagram. At the end of the tie lines, you will have the composition of the oil or of the lutidine and the water-rich phase. And now you can actually, for each tie line, plot the interfacial tension against the temperature here. And then you see at the beginning, at the critical point, of course, the interfacial tension is 0. But as you increase the temperature, the interfacial tension will increase. What does that mean for the colloids that attach? Well, say you have a colloid of 200 nanometer radius at, I think, 60 degrees here. It will have an attachment of 24,000 times its thermal energy. So you can see from this very large attachment energy that the particle is irreversibly attached and thermal motions will not be able to bring it off the interface. And this is why such colloids can actually form such a densely packed layer at the interface that even allows the interface to be curved into non-equilibrium shapes. But now imagine you take smaller colloids that only have a radius of 10 nanometer and you calculate the attachment energy. Here you get only 61 times the thermal energy. That's substantially lower than what you get for this larger colloid. It still is pretty high compared to the thermal energy, but in such interfacially jammed layers, there are also lateral mechanical stresses that can cause the colloids to be pushed out of the interface. And usually 60 kT of attachment energy are not enough to hold colloids there in such a jammed configuration. So is there a way to use also nanoparticles to have a very stable bijel structure? Yes, there is. And to make this work, we actually need to use a ternary liquid system instead of a binary liquid system. Here is the ternary diagram of water, isopropanol, and an oil that I call just DEP. Also there, you have regions of nucleation and spinodal decomposition. Just now, instead of the temperature as the indicator for what interfacial tension we have the solvent fraction going here from 0 to 50%. I'm now plotting the interfacial tension against the solvent fraction. And as we quench the system from the miscible region to the immiscible region, we decrease the solvent fraction from 50% to 0, going from right to left here. And the interfacial tension will increase up to 16 millinewtons per meter for this specific example. At 16 millinewtons per meter interfacial tension, even for 10 nanometer particles, you get an attachment energy in the orders of thousands of kT, so significantly higher than what you can get with binary liquid mixtures. And that's the reason, at least I believe, why in our lab currently we are able to make these bijels with nanoparticles, which allows us to give them nanostructured fluid-Bicontinuous channels. While with binary mixtures, you need to use large colloids that also result in very large bijel channel dimensions. Good. So now you've already seen a little bit about these nanostructured bijels formed via STHIPS. So let me tell you a little more about that. What you see here is a ternary, this triangle, and that triangle actually describes the miscibility of oil, water, and a solvent. So on one axis the water, on the other the solvent, on the other the oil. I always make this joke, you know how it is with oil and water, they don't mix. It's just like students and professors. But there's one thing that mixes them, alcohol. You can mix students and professors and as well oil and water with a good amount of alcohol. This is exactly what happens here. We use alcohol as a solvent. And then, for instance, you have that point here in the ternary phase diagram. It has 60% alcohol and 20% water and 20% oil. That's enough to mix oil and water, 60% alcohol. But that point here, it only has 30% alcohol. That's not enough to mix 40% of water with 30% of oil. So what will happen? This point, it's going to split into two phases, one rich in water, the other rich in oil. And that can happen, for instance, again, via spinodal decomposition. So what we do to trigger spinodal decomposition, we prepare a homogeneous mixture above the binodal. We inject that as droplets into a stream of, for instance, water. Those droplets then will lose the solvent that's in them. That will cause the oil and the water to phase separate within the droplet. So here you see a video of this happening. This is taken with a high-speed camera. You see the time scale. These are droplets pinching off a nozzle where this ternary mixture flows out, and then you see the patterns really indicating the phase separation of oil and water. That's why we call this solvent transfer induced phase separation, abbreviated as STRIPS. The solvent diffuses out of the droplets, triggers phase separation. So here, this happened just with the liquids alone. And at the end, the phase separation will cause complete phase separation eventually. What we do is we add these nanoparticles alongside with an oppositely charged surfactant. The surfactant adsorbs onto the particles and renders them interfacially active. Without the surfactants, the particles would prefer to be in the water. They would not be interfacially active, but the hydrophobicity imparted by the physisorption of the surfactant makes them hydrophobic. And then you can see that the droplet pinch-off looks very different. Now, instead of these nice spheres, you get these blobs, and they actually can retain their shape as they travel down the channel. If you tune the conditions a little more, you can extrude actually infinitely long fibers of these nanoparticle containing ternary mixtures. And yeah, what is probably going on here is now you can see how the patterns indicate spinodal decomposition. The particles are forming a gel within the phase separating mixture that then arrests the structure. And here you see this happening live in the laboratory, where this fiber is traveling into a container filled with water, and then it coils down and sinks at the bottom and heaps up as an infinitely long fiber collection. You can also print these fibers in the laboratory, or also here you get an impression of the printing process, basically. You can collect them in a rotating container. They will sink down and land at the bottom. Or here you can also collect them on a rotating underwater spool, for instance. So again, the important trick was the surfactant makes the particles hydrophobic. And now I also actually have a fluorescent dye that allows me to see the particles in the microscope that I'll show you later. So here you see a little how the weight percentage of nanoparticles, this is, you can't really see it because this column is in the way, but how with increasing weight percentage of nanoparticles, you can structure these fibers to get smaller pores. And interestingly, also with increasing the surfactant concentration, you can reduce the pore size of these fibers. Nevertheless, if you look inside of these fibers, right, these are confocal microscopy reconstructions, then you see they actually really only look like a fluid-bicontinuous network on the surface. But on the inside, they have like a less well-defined structure. So this indicates that on the surface, this nanoparticle stabilization has worked very well, but deeper inside, not so well. That has been a question that has been driving me for a long time. Why can't we stabilize also the spinodal decomposition deeper inside of the fiber? It has been haunting me for years. And finally, we have also succeeded in doing this. This here you see is an experiment, a very simple experiment, where we make one of these fibers just with a pipette in the laboratory, and then it sinks to the bottom and it lands on this glass slide. Then we can put it onto a confocal microscope. And with a confocal microscope, you can scan through this material, as you will see here. We take a so-called Z-stack, where we scan like a tomograph through the material, and then we have fluorescent labels, one that labels the water in magenta, the other that labels the particles in green. And you can see this scan here shows that the bicontinuous fluidic network within this fiber is extending from the surface deep into the material. So this was our first time we succeeded in actually having such a well-defined bijel made by a solvent transfer-induced phase separation. So how did that happen? That's kind of what I would like to tell you about now in the following slides. Why do we obtain such a well-defined bijel with this specific system? So what we have as a ternary liquid mixture is water, 1 propanol, and this oil that I abbreviate as DEP. Here you see the chemical structure. The nanoparticles have been functionalized by these alkyl ammonium bromides, and there's also a fluorescent dye that makes them green. Now, we simply start with that mixture at the critical point that has the particles. We flow it into a bath of toluene, and the 1 propanol, it diffuses into the toluene and triggers phase separation. Now, we did the same experiment, this time with 2 propanol instead of 1 propanol. And with 2 propanol, we were never able to get such a well-defined bijel. Instead, you have again a gradient in pore size with small pores on the surface and large tens of micrometer sized pores deeper inside. Why does 1 propanol make such well-defined bijels and 2 propanol not? So let's try to analyze that. What's the difference between 1 and 2 propanol? Let's first think about generally how this happens, the STHIPS process. So here you see a cross-section of the fiber, and the solvent transfer initially starts at the surface of the fiber, right? And then phase separation takes place there, while inside it's still not phase separated. But over time, the diffusion of the solvent also will cause the deeper inside structures to phase separate, and eventually all the solvent goes out. Apparently, for 1 propanol, that results in a really well-defined bijel, but for 2 propanol, not. What's the difference? So we need to look at the ternary phase diagrams. Here you see the ternary phase diagram for 2 propanol, water, and toluene, which is the surrounding fluid. It's a fairly symmetric phase diagram. That means the critical point is kind of in the middle, and the tie lines are almost horizontal. The tie lines being horizontal means that 2 propanol partitions equally well between toluene and water. In contrast, the same phase diagram with 1 propanol is less symmetric. Now, the critical point is shifted to the side, and that means the tie lines are more inclined. That means that 1 propanol prefers to partition to toluene over water, right? So during STHIPS, we start here, and over time, the solvent diffuses out. And as you see before, the interfacial tension increases. So Azim is a PhD candidate. He measures the interfacial tension in a pendant drop tensiometer. So what Azim here did, he prepared equilibrium mixtures that are immiscible and measured their interfacial tension, both for 1 and 2 propanol. So he first selects an arbitrary composition on one of these tie lines and lets it phase separate, and then takes the oil-rich phase and the water-rich phase in separate vials. And then he forms a droplet of the water-rich phase surrounded by the oil-rich phase. He takes a picture of the droplet, he fits the Young Laplace equation and obtains the interfacial tension. Now I'm going to plot the interfacial tension for these tie lines in this diagram here. You see from the color code, magenta to dark blue, that means we're going down the phase diagram. So at the higher up tie lines, the interfacial tension is really low, right? But down here, the interfacial tension is higher. Now you see for 1 propanol, that's this system, the interfacial tension goes up more at a more steep incline than for 2 propanol. Okay. Now we have this experimental data. Let's do a COMSOL simulation that's just using Fick's law of diffusion for transient conditions to estimate the solvent concentration in this fiber segment over time. And what we found is that for 1 propanol, the solvent goes down faster than for 2 propanol with time. And now we can combine the known or simulated volume fractions of propanol in the fiber with the interfacial tension to obtain this graph. It estimates how fast does the interfacial tension increase with time for the system of 1 versus 2 propanol. And we find that for 1 propanol, the interfacial tension increases more rapidly than for 2 propanol. And you remember the formula of the attachment energy for the particles. The higher the interfacial tension, the higher the attachment energy. So what that means, for 1 propanol, the attachment energy will reach about 1,000 of kT within a few hundred milliseconds, while for 2 propanol, it takes seconds for it to reach several hundred or almost 1,000 kT. So this was for us one of the first explanations why 1 propanol makes such a well-defined bijel, while 2 propanol does not. But I have to tell you that this is not the whole story. So this was just one part of the story. So our indication was the interfacial tension and attachment energy of the 1 propanol bijel is more rapid, and therefore the stabilization will take place at an earlier stage of the phase separation. But there's a second component. It's the functionalization of the particles with the surfactant. So again, 2 propanol makes such a hollow, ill-defined bijel. When you look at the confocal micrographs, you see the green particles, they have formed an interfacial film around the magenta water domains, right? These are water domains. But you also see that there are additional fluorescently labeled particles inside the water domain. The particles are also forming an interfacial film, but this interfacial film comes with additional aggregated particles that are in the oil domain, not as for the 2 propanol system in the water domain. You see the green fluorescence is in the black region. That means the particles are in the oil. So it seems that for 1 propanol, the particles partition into the oil during the phase separation, and for 2 propanol, the particles partition into the water during the phase separation. So why is that happening? So I told you before, the surfactant makes the particles hydrophobic, right? The more surfactant is adsorbed, the more hydrophobic the particle is. Maybe this particle is modified so that it is not really hydrophobic, it still is preferring the water, but has a mild wettability for the oil. Such a particle with a contact angle smaller than 90 degrees typically stabilizes oil in water emulsions. On the other hand, if you have a particle that is really hydrophobic, that prefers the oil, then you get water in oil emulsions. Now, only with particles that have a contact angle close to 90 degrees can you actually stabilize interfaces that have curvatures in both directions. So experimentally, we find that we need a specific concentration of this surfactant to get a well-defined bijel, which indicates that at that concentration, the particles are able to obtain a contact angle close to 90 degrees. So Catherine is a postdoc, and what Catherine measures is what kind of emulsion do we get for a given CTAB concentration. So what she does, she prepares, again, like Azim, equilibrium immiscible mixtures of oil and water, and then she does that at a specific concentration of the surfactant and the particles, and she just then vigorously agitates it, and she sees, is it a water in oil or an oil in water emulsion? And what Catherine finds is that above a concentration of around 25 millimole of this surfactant, you get water in oil emulsions, and below oil and water emulsions. That indicates here again that the surfactant modification at 25 millimole is suitable to provide a contact angle close to 90 degrees. That means below that concentration, you get oil and water emulsions, and above you get water and oil emulsions. And just at the boundary, you have the right functionalization needed to make a bijel. With 2-propanol, on the other hand, you always get oil and water emulsions. That indicates the particles for 2-propanol are always too hydrophilic. They don't reach the suitable functionalization to stabilize the bijel. Why is that difference between 1 and 2-propanol for the partitioning of for the contact angle? It originates from the partitioning of the surfactant. The surfactant CTAB has a partitioning coefficient that tells you how much of the surfactant is in toluene and how much of it is in water. So if K is larger than 1, then more of it is in the toluene. For 1-propanol, we find that the partitioning coefficient can be larger than 1, while for 2-propanol, the partitioning coefficient of CTAB is always below 1. That shows that because of the propanol, the 1-propanol, partitioning into the oil-rich phase, the toluene-rich phase, also the CTAB partitions into the oil-rich phase. And as a consequence, also the particles partition into the oil-rich phase. And that's part of the mechanism why these 1-propanol bijels are stabilized so efficiently with 1-propanol. To a short mini summary. Again, you've seen it makes quite a big difference what solvent you use doing STHIPS. So we obtained smaller bijel structures with 1-propanol because 1-propanol partitions to the oil-rich phase. On one hand, that results in a faster increase of the interfacial tension. And on the other hand, it facilitates contact angles of the nanoparticles that are close to 90 degrees. These results were just recently published in this paper that's, or it has just been accepted actually, but I think the online version is already there. So if you're interested, you can take a look. Third part of the talk, how to flow fluids through bicontinuous gels, fluid-bicontinuous gels. In order to do this, we actually first need to reinforce the bijel by cross-linking the nanoparticles at the interface. So this is a little bit of chemistry. So we have a chemical that is called Theos, and it is in the oil phase, and it hydrolyzes to form silica. And that silica, what it does, it binds the particles at the interface to each other so that they are not only held by interfacial tension, but really mechanical or like chemically bound to each other. And that makes the bijel more robust. You can wash away the oil and the water, for instance, and dry it, and so that everything is gas and silica, and then still stable. And again, this phase separation takes seconds, right? But this cross-linking actually takes hours. So it's a long-time chemical reaction that was first published in this work here. And that way you really obtain these fibers that can be dried, and where you can like see really the silica scaffold that was assembled by the phase separation of oil and water. So Paolo already mentioned I have a ERC starting grant, and my ERC starting grant actually focuses on this idea. Here you see a cut through one of these bijel fibers where I opened the inside, and you see it's not one of these well-defined bijels, but one that has more like large channels. And now think about it. The oil and the water, they are arrested by these nanoparticles. Now, if you have an oil-soluble reactant A, for instance, an alkene, and a water-soluble reactant B, like hydrogen peroxide, they can meet at the interface to undergo a chemical reaction, for instance, to produce an epoxide here. Epoxides are high value-added chemicals. They are used for glues or for other precursors, for plastics, etc. And my idea is to continuously flow the water-soluble and oil-soluble reactants through this structure and then collect the products by flow chemistry. So that would be a continuous flow biphasic catalysis. So what we do, we assemble these bijel fibers in a device, and then we flow reactant A in. It travels through the fiber and comes as a product out because the other reactant has traveled around the fibers. But for this to work, we first need a way to flow the reagents through the fibers, right? And that's the project of Alessio. So Alessio uses electroosmosis to flow water through the bijel structure. But for electroosmosis to work, the silica particles, here fluorescently labeled in green, need to have a surface charge. When we make the bijels, that is at pH 3, the silica surface is usually not charged because most of the silanol groups are protonated. But we increase the pH and then deprotonation of the silanol groups takes place and we obtain negative charges on the silica surface. And you can see this actually here with a fluorescent indicator that shows that at pH 3, there's no fluorescence, but at pH 9, blue fluorescence shows up, which is showing that the pH within the bijel has indeed increased by the addition of a base. So then we have our fibers here, we connect water droplets at their ends, and we cut open the ends, and then we submerge electrodes and we apply a voltage. And over time, the positively charged counterions above the silica will move towards the negatively charged electrode. Along their way, they drag water with them, and thereby the water reservoir that was big here is small at the end because all the water has been transported here. So you see this happening here. Here, the water reservoir, number one, the other water reservoir, and you see how this reservoir over time increases in size because the water is really flowing via electroosmosis through the fibers. Good. So you can measure now the volumetric flow rate of water through the fibers against the applied electric field. You can also show that a fluorescent dye can be transported from one end of the fibers to the other via this electroosmosis. And then you can use this for an application where we separate a chemical from the oil that surrounds the fibers into the fibers. So we flow water through the fibers, and then we place I call it flow device above the fibers. We let oil, dodecaine, with alcohol flow in, and then it will flow over the fibers, and the remainder of the dodecaine with alcohol comes out. And along the way, the alcohol goes actually from the dodecaine into the water of the fibers. It is being extracted by the fibers. So the goal is to kind of collect the ethanol in this water reservoir because electroosmosis has transported it from one side to the other during the extraction process. So first of all, let's design this system, and we again use COMSOL to model the fluid dynamics here. You see the streamlines with a color coding giving the fluid velocity of the dodecaine flowing over the fibers at the inlet and the outlet. And in red underneath, you can see the streamlines of electroosmosis in the fibers. And if you now, yeah, you see with increasing the voltage, more water flows through the fibers and the concentration of ethanol in the surrounding will decrease further. And then you can actually measure the amount of ethanol that has been extracted into the fibers, here shown with blue data points, and in black I show you the COMSOL simulation that we've done, and they agree reasonably well, showing that really the diffusive mass transfer of the and convective and diffusive mass transfer of the ethanol into the fibers is driving this extraction process. That was basically most of what I really wanted to tell you. The rest is more about hydrodynamics, but I think for the sake of time, I will skip this part and just arrive at my summary and conclusion slide, for which I again swap here. So you've seen how we can use strips to make these nanostructured bijels. We've actually managed to flow fluids through bijels via electroosmosis, and that has then been used for continuous flow, liquid-liquid extraction. I didn't tell you about that, but we also found a way to make ropes via microfluidic twisting. This is my research group. The wiggling pictures are showing the people that did most of the work that I showed you today. I acknowledge the funding of the European Research Council and the Dutch Science Foundation, as well as the American Chemical Society, Utrecht University and Rouen University, and you, of course, for your kind attention. Thanks a lot.
Okay. Okay, thanks very much, Martin, for a fascinating seminar. And it's now time for questions. So who wants to ask a question? Nuno's here.
And Martin, thank you very much for your talk. Very interesting, and even more interesting is the system. So I have two questions, but they are somehow related. My first one is related to the degree of control over the connectivity properties of these two entangled networks that you have, right? And in particular, thinking about the application that you have in mind of having two fluids flowing, one of the things that is important is to guarantee that you have percolation of both networks. But the second thing is related to the efficiency of this idea of having a reaction between something that is immiscible in water and the other in oil at the interface between the two. And again, the level of connectivity is important for two reasons. First, because you need to have very narrow channels, so you need several channels, but also you want to avoid to have dangling ends, right? Because the transport is only through the backbone. Yeah. So how can you control these things? And if you have already think about that.
Yeah.
Thank you.
Yeah, so experimentally, I mean, it works quite, we usually don't see really dead ends. Let me show you the confocal micrograph again. If we control it by varying the different parameters, such as the nanoparticle concentration, the surfactant concentration, and then usually we do this kind of like a trial and error on a trial and error base, where like we prepare the sample, like you see here, with a pipette, we make one of these fibers, we collect it in this container, put it to the confocal microscope, check the structure, and then analyze, can quantitatively analyze the connectivity in 3 dimensions also. And usually there are no dead ends when the suitable composition is chosen. So that's kind of just experimental like methodology that is needed. And it's to your second question about the efficiency. Yeah, so I like such chemical reactions that take place between immiscible reactants. You can also carry them out with emulsions. Like you can shake one phase and the other, that forms droplets, and then the droplets may be stabilized by also particles. But the problem is, if you carry out this droplet-based reaction, eventually the reactants that were in the droplets will be depleted at some point. And then you need to separate the droplets from the continuous phase and harvest your products. Here, the idea is to have not to do this by just continuously flowing in and out. I find this concept also of particles at the interface as heterogeneous catalysts very interesting, because the particles, basically the contact line, the three-phase contact line, where both the oil and the water are touching the particle surface, that to be really this location where the immiscible reactants can undergo the chemical transformation, very fascinating. But again, this is really work in progress still. We just manage to do this extraction, for us, the next step is to really introduce catalytic particles into the bijel.
Yeah. But the fact that you need to reduce the size to something of the order, you showed something with slightly above 10 nanometers, as far as I can remember. Mm-hmm. Then this is also working as a barrier at the interface mm-hmm. for the reactants to meet, right?
Yeah, but it is somewhat a barrier indeed. It's not a free liquid-liquid interface. There's like a, maybe in first approximation, hexagonally packed mm-hmm. layer of particles. Of course, the only places where the exchange can happen are the interstitial spaces between the particles at the interface. One could also envision to use porous, mesoporous particles, for instance, where there would then be more liquid-liquid interfacial area available.
Yeah, but the fact that you have a flow with the porous materials, you will need to wait enough time for them to diffuse, and this will compete with the advection, and therefore I don't know.
Yeah, but so think about it, like in our system, the way how we carry this out is typically the flow takes place in this direction, in axial direction of the fiber. That's the long, centimeter long distance to travel. The diffusion takes place in radial direction. Mm-hmm. So this is only 25 micrometers in radius. The diffusion happens in milliseconds for this.
Okay. Yeah. Good. Thank you very much. Great talk.
Thank you.
Okay, very good. Thank you. Next question from Maria.
Thank you. Very nice talk. Thank you, Martin. So I have a kind of general question to you. So these bi-continuous phases were already known in ternary mixtures of oil, water, and surfactants. So here you would just, correct me if I'm wrong, you were just having more control over the surfactants. Yeah, in some sense, you have nanoparticles with some surfactants attached to them. So it's really, you can get more control over these phases, isn't it?
Maybe not actually. It's just because it's a non-equilibrium assembly process.
Okay.
A history-dependent non-equilibrium assembly process.
Okay. So in the case of the usual ternary mixtures of oil surfactants, they were equilibrium phases with binary two domains, two percolated domains.
Yes.
So that's the one difference. Yeah.
That's a big difference. This is this would be an equilibrium system. The micro emulsions, right?
Micro emulsions, yeah.
Their entropy drives the formation of the bicontinuous arrangement, and it's a thermally fluctuating system. While this here is a static system.
Okay.
Yeah.
Okay.
Yeah.
Okay, thank you. And then another question is more technical. When you introduced the ternary mixtures diagram and you plotted the interfacial tension energy of the particles, it seems to me that you had the maximum of this interfacial energy when you didn't have a ternary mixture. So it's really one of the first slide where you introduced the ternary mixture.
Yeah. Let's see.
It's not very important.
No.
It's below. I think.
Yeah. Okay. Let me make it in a slide.
More visual. Yes. It's here now. I think the next, if you plot it, So you have the maximum surface tension when you go to 0 EPA volume fraction.
That's right. Yes.
So why it's a bit confusing to me. So because you want to maximize this interfacial tension, isn't it? So you can reduce the size of the nanoparticles.
That's right.
Still get so you have kind of compromise here.
Yeah.
So it's okay.
Yeah, it's true. We want this value to be high so that the attachment of particles comes with a high attachment energy.
Yeah.
Over time, it increases the interfacial tension because the two phases, they become more different in their compositions.
Okay.
The oil phase becomes more pure oil,
Pure.
the water phase becomes more pure water because the solvent is removed. Initially, both the oil-rich and the water-rich phase both still contain substantial amounts of the solvent. And that causes them to have a low interfacial tension.
Okay.
Yeah,
Okay,
so there's actually, I wish it would immediately get a high interfacial tension, because then the nanoparticles would be very efficient in stabilizing the structure right away. I think with the system of 1 propanol versus 2 propanol, we have approximated this situation, because when you look at the phase diagrams of 1 versus 2 propanol here, you see the tie line is so steep, and that means that the oil phase and the water phase are very different in composition. That gives it a higher interfacial tension right away.
Okay. Thank you. Thank you.
Thank you.
Okay. Okay, very good. Do we have any more questions? I don't see any more raised hands. So I think it's time to wrap up. It's getting on 12 o'clock our time, 1 o'clock your time. So Martin, I think you're free to have your lunch now.
I already had.
Oh, you already have. Okay. Okay. Very good. Thanks very much, Martin, for a fascinating seminar. Thanks to all for coming, and
thank you.
And we'll see each other again at some conference or other in the future. I'm sure now that conferences are taking off again, I'm sure we'll be meeting somewhere sometime.
I hope so too.
Yeah, absolutely. So recording stops now. How do I stop this? Oh yes,
Bye-bye, Martin.
little button at the bottom.